green line, which shows that how entanglement entropy of Hawking radiation evolves in time from the time when a black hole was formulated from the collapsing matter to the time when a black hole completely evaporates by Hawking radiation. So if you believe Hawking semi-classical computation, the entanglement entropy of Hawking radiation actually monotonically grows forever until black hole completely evaporates. However, if you require underlying mechanics is actually a underlying quantum mechanical process is unitary, then the entanglement entropy of Hawking radiation should behave like this curve. So this curve is a page curve, and there should be some transition in the middle of evaporation, and this transition time is called page time. So of course, if you use something like holography, like ADS-CFT, the boundary CFT, of course, you get this type of curve for evaporating a black hole. However, it was very challenging to get this curve from a purely gravitational point of view. So this was achieved by the island proposal. So this right-hand side diagram shows a Penrose diagram of evaporating black hole, and this brown region corresponds to the collapsing matter, which forms a black hole horizon, which is denoted by this orange line. And this weakly blue line is a black hole singularity, and because of the Hawking radiation, this black hole actually completely evaporates at some time. So island formula basically tells us that there is some non-trivial quantum extremal surface, which I'm not going to talk about detail, but such island region appears inside of a black hole at a later time, and such island region actually purifies Hawking radiation, so that from a gravitational point of view, we can actually recover this page curve. So this achievement of constructing page curve from a gravitational point of view is very important. But there was also another important development for quantum gravity theory was also achieved by studying lower dimensional quantum gravity theory recently. And that is a discovery of a new type of ADS-CFT correspondence, which includes some kind of ensemble average for the boundary theory. So, this is pretty much related to our work. So let me give a little bit more detailed explanation for these new types of ADS-CFT correspondence. So this new type of ADS-CFT correspondence was originally discovered in the Jackiw-Teitelboim gravity theory, which is a two-dimensional dilaton gravity theory. And especially this theory is very interesting if we define the theory on Euclidean signature with a negatively curved background. So in this talk, I will solely focus on Euclidean signature with a negatively curved background case. So in that case, the action of this JT gravity can be written in this expression. So the first part basically corresponds to the Einstein-Hilbert action. But as you know, Einstein-Hilbert action in two dimensions is just topological. So on shell, this part of Einstein-Hilbert action just gives the Euler characteristics of the background manifold M. So just to clarify notations here, S naught is just a large parameter which gives topological suppression when we later consider topological expansion. And then we denote two-dimensional manifold M, and whose boundary is denoted by delta M. And G is the metric for two dimension, R is the Ricci scalar for two dimension, and H is a boundary induced metric, and K is a boundary extrinsic curvature. And this field phi is a dilaton field. So besides this Einstein-Hilbert action, the second part is basically the dynamical part of JT gravity. But as you can immediately see, the dilaton field for the bulk action, dilaton field just appears linearly. So this dilaton field is just Lagrange multiplier, which enforces R equal -2. So the background is constant negative curved background. And because the bulk action is just linear in this dilaton field, on-shell action solely comes from this boundary term. And this boundary term gives the so-called Schwarzian action, which we will explain later a little bit more. So the action is defined by this equation. And if we define the theory, for example, if we define a partition function of JT gravity by summing over all higher genus topologies, so which starts from just disk, but includes this one genus contribution and the two genus contribution and so on. And if we define a partition function in this way, actually it turns out that the dual theory of JT gravity is actually a random ensemble of some quantum mechanical system rather than a specific quantum mechanical model living at the boundary. So of course you can also define the theory or model by different way. Namely, we just fix background topology. So, for example, if we just focus on this disk geometry, then the boundary theory is purely given by Schwarzian theory, which comes from this boundary action. But if we define the theory by a topological expansion like this, then the boundary theory is a random ensemble. So as we saw in the previous page, actually for JT gravity, physical degree of freedom purely comes from the boundary term. And this boundary term can be written in terms of Schwarzian action or Schwarzian theory. So we can actually decompose higher genus contributions into two pieces. So the leading topology was Poincare disk, which is described by SL2R Schwarzian theory. While for higher genus contributions, we can artificially split into two pieces. So this picture is for genus 2 contribution. And only physical degree of freedom are located at the physical boundary of this manifold. So these wiggly lines represent physical degree of freedom. And we can formally cut in the middle here. And then physical degree of freedom solely comes from this right-hand side topology, which we sometimes call trumpet geometry. So the Schwarzian theory defined on this trumpet geometry actually breaks original SL2R global symmetry by this hole down to U1 global symmetry. So the corresponding Schwarzian theory for this topology is given by a U1 hyperbolic Schwarzian theory. So formally, we can write down the previous genus expansion, this one, in the following expression. So this e to the s naught comes from the Einstein-Hilbert action, and which had Euler characteristics. So this factor actually suppresses all higher genus contribution. But we can write down all contribution in this way. So the leading topology comes from disk geometry, and we denote the partition function of corresponding Schwarzian theory by this G disk Schwarzian. And then whole higher genus contribution, we split this non-physical modular volume contribution. And this volume contribution is denoted by this B, and the physical degree of freedom solely comes from this trumpet Schwarzian theory, and whose partition function is denoted by this Z trumpet Schwarzian. And we artificially cut it here. So the parameter B is a geodesic length of this cut. So we have to integrate over all possible B, which is a positive real number. And this measure factor B comes from basically twisting these two holes to each other. And generically, we can also consider n boundary cases. So we call such a contribution n-point function of a partition function. So formally, we write down, of course, we are interested in connected pieces, because disconnected pieces are solely can be constructed by just connected contributions. So so for this n-point function of a partition function, we can also write down a formal topological expansion in this way. And the coefficient z of Gn, for example, when genus is 2 and n is 3, n represents boundary, number of boundary. So 3 boundary with 2 genus case, the corresponding topology is like this picture. And again, for these components, we can also cut boundary degree of freedom away from the all genus contribution. So this G of Gn, we can again write down in terms of trumpet Schwarzian partition functions with this volume element, volume factor, V of Gn, and then we integrate over all cuts we artificially made it to get this expression. So as we saw in previous pages, physical degree of freedom comes from solely by the JT gravity theory defined on disk geometry or trumpet geometry. So it's nice to look at these cases more closely. So again, the JT gravity action is given by this expression. Here I excluded Einstein-Hilbert action, which just gives topological suppression factor. And as we said before, the variation of phi leads to R equal -2. So Einstein-Hilbert action are just reduced to Euler characteristic chi. And actually the on-shell, so the variation of phi leads to this equation for each scalar, but we also have a equation for dilaton field, which comes from variation of metric. And we need to solve these coupled equations. And it turned out that on-shell geometries are only two geometries given by disk geometry or trumpet geometries. So for these two geometries, we can take metric in these forms, and the corresponding dilaton solutions are given by these Koch or Shinch form. So this gamma factor, the constant factor, which remains arbitrary at this point. So now the periodicity of angular coordinate for disk geometry, this phi, the periodicity is 2 pi, as we expected, but this angular variable tau for trumpet geometry has a periodicity b, and b is about geodesic length of the other artificial cut we made here. So this periodicity of tau actually breaks this original SL2R global symmetry, which is a global symmetry of Euclidean ADS2 or hyperbolic space down to U1 symmetry, which is basically just rotational symmetry around this hole. So, okay. Okay, so as we said before, the bulk action was just linear in dilaton, so this does not give any contribution to the on-shell action, and on-shell action solely comes from the boundary term, and the boundary term actually rewritten in terms of Schwarzian action. So here, so I will actually explain a little bit more detail how to get these actions, but here we expressed bulk angular coordinates theta or tau in terms of boundary time u. So I will explain how to get these expressions, but here let's just assume we get these actions. And then the corresponding, so this is a Schwarzian derivative, as you know very well. Then the corresponding partition functions are given by these expressions. So for action part, I explicitly expanded this Schwarzian derivative and did several integration by parts to write down this expression. And I'm not explaining in detail, but there is some measure factor also included by this mu here. And then finally, we also need to divide by gauge volume corresponds to the each global isometry SL2R or U1 factor. So this gives a physical degree of freedom. So the remaining factor is non-physical modular volume factor, which is this V noble Gn. And this volume is called Weil-Peterson volume. And I'm not going to explain detail, but in mathematical literature, this gauge, this modular volume actually satisfies some topological recursion relation. And the topological recursion relation written explicitly in terms of resolvent W. So W is a Laplace transform of this V. And for each is B, transformed to this Z. So in terms of this resolvent W, the recursion relation is given by these expressions. So this recursion relation requires input for W01. So W01 corresponds to one boundary zero genus contribution. So in terms of JT gravity, this Y corresponds to the spectral density of disk partition function. So if you give this disk spectral density, then this recursion relation automatically gives you all higher genus contributions. So for JT gravity case, the leading disk geometry spectral density is given by sine 2 pi z over 4 pi. So if you put this input into the recursion relation, it gives you all higher genus contribution. And some explicit solutions are given for some of these lower contributions. So these W are related to Weil-Peterson volume V by Laplace transform for each parameter B, like this expression. And indeed, it turned out that this recursion relation was actually originally found in the matrix integral literature. So for matrix integral, we define by this path integral, we have a random n by n matrix H. So we integrate over all elements of this random matrix H with a weight factor given by this expression. And in this theory, we define endpoint function of loop operators. So loop operator corresponds to this trace of e to the minus L times this Hermitian matrix H. And endpoint function of this loop operator can also written in terms of large n expansion. In the large n limit, this expansion can be written in this large n expansion. And each these Gn actually match with the all corresponding JT gravity results defined like here. So by this matching, people claim that JT gravity defined by summing over all higher genus topology is actually dual to one Hermitian matrix integral defined by this path integral. So this is a kind of motivation for our work. So now let's move on to our paper. So, but just before that, in the previous discussion, we saw that this trumpet geometry plays a crucial role for constructing topological expansion for JT gravity. So it's interesting to study other topologies as well. And also this this trumpet geometry is actually related to the so-called puncture disk geometry, which is just hyperbolic disk geometry with a conical deficit angle inserted at the center of this disk. By simple analytical continuation of this parameter, B to I alpha. And this alpha is a conical defect angle of this puncture disk. And also, Riemann surfaces with conical singularity naturally appears when we generalize dilaton potential of JT gravity to some exponential form. So this motivates us to study JT gravity with a conical defect angle. This is the rest of my talk, but maybe this is a nice timing to pause if you have any questions for previous discussions. Okay, if not, let's move on. So this is the rest of my talk. So first, I will introduce the formation of JT gravity by generalizing dilaton potential to some exponential form. And then next, I will try to explain how such JT gravity can be written in terms of a standard quantum mechanical system of a charged particle with a background magnetic field. And then we solve such quantum mechanical system. And finally, we will also discuss some topological entanglement entropy. And then finally, some conclusions. So let's define our generalized JT gravity action. So again, I will focus on Euclidean signature with a negatively curved background case. So the entire action has the same expression as before, except this dilaton potential. We now generalize to a general function form of dilaton field phi. So the first line is again the Einstein-Hilbert action, and then the second line corresponds to the dynamical part of this modified JT gravity action. And in the rest of my talk, we will be interested in the particular form of dilaton potential W, which starts from 2 phi. So if we just truncate all higher order contributions and focus on just this 2 phi contribution, and then and then this contribution gives the original JT gravity action. But here we include additional term which has exponential of minus alpha times this dilaton field phi. And we are interested in, so this epsilon is just a small expansion parameter. And in this talk, we are interested in the zeroth order and the first order in this expansion parameter alpha. Expansion parameter epsilon. And then this alpha is related to the conical defect angle. I will explain soon. So in order to deal with this parameter epsilon, we expand in epsilon for the integrand of path integral. So because we are interested in Euclidean signature, the integrand of path integral is given by exponential minus action. And then for this action, we expand in epsilon. So the zeroth order corresponds to the original JT gravity action, which is denoted by this I naught. And then the epsilon appeared in the potential term gives this expansion in the integrand, not path integral. So as we said before, for zeroth order of this parameter, epsilon corresponds to the original JT gravity action. So again, we have R equal -2, and then on-shell action has this topological contribution coming from Einstein-Hilbert action plus this boundary contribution. And then on-shell geometries are this disk geometry and trumpet geometries. Corresponding background solutions are given by this expression. So for next order in epsilon, the first order in epsilon, we exclude this integration over x1 outside of path integral. And then we combine this exponential factor together with this zeroth order action, which leads to this first order action, which has almost the same form as the original JT gravity action, except this minus alpha phi x1 term, which comes from the previous expansion in epsilon. So now, because of this insertion at x equal x1, the variation of phi now leads to r plus 2 equal some delta function contribution comes from this insertion. However, besides this insertion point, x equal x1, we can still have Euclidean ADS2 geometry. So we take the same form of metric as we had for standard standard Poincare this case. But because of this defect insertion, the periodicity of angular coordinate is now reduced by this alpha, so that the periodicity is now given by 2 pi minus alpha. But the on-shell action can also be written in the same form, which has topological contribution comes from Einstein-Hilbert action plus boundary contribution. So the standard way to deal with physical degree of freedom is to introduce Schwarzian action. So to do so, we first need to fix boundary condition. So the boundary condition we use here is the standard Dirichlet boundary condition for ADS-CFT, which means that so more specifically, we introduce boundary cutoff at rho equal rho naught, and eventually we will be interested in rho naught to infinite limit. And then we fix the value of metric and value of dilaton field on this boundary cutoff at rho equal rho naught. So we denote the boundary value of dilaton field at this boundary cutoff by phi b. And fixing a metric on this boundary cutoff means that we fix the angular coordinate of the bulk geometry at this boundary cutoff. So we take this value of angular coordinate at this boundary cutoff by this combination phi b times u, and we regard this u as the time of boundary theory. So as we said before many times, boundary action is only physical degree of freedom. And now if we regard the bulk angular coordinate phi as a function of boundary time u, and then if we evaluate this extrinsic curvature and taking rho naught to infinite limit, this gives the Schwarzian action, which is given by this expression. However, we can also formulate the physical degree freedom in another way. So this is to rewrite the boundary action in the form of standard quantum mechanics of a charged particle with a constant background magnetic field. So the corresponding action is given by this expression. So how do we get this expression? Well, first we use Gauss-Bonnet theorem to rewrite this extrinsic curvature contribution we had here. So Gauss-Bonnet theorem gives us some topological contribution, again proportional to this Euler characteristic chi times this delta phi. Delta phi is a periodicity of this angular coordinate phi. Plus this Gauss-Bonnet theorem gives this area contribution. So area is defined by this two-dimensional volume integral. And we had also this -1 contribution here. So this -1 is basically just counter term, which cancels some divergence contribution comes from this extrinsic curvature when we take this rho naught to infinite limit. But anyway, this counter term -1 part simply becomes this length of boundary circumference, so which gives this Lm, and then the total of boundary action is given by this expression. Here we renamed this boundary value of dilaton field by Q, because this Q basically becomes the charge of this quantum mechanical charged particle. And then boundary inverse temperature is related to the boundary circumference, this Lm, by some regularized way. So next we defined now we defined this action, and I said this action represents a standard quantum mechanics of a charged particle with a background constant magnetic field. So in order to see such constant background magnetic field, we look at area term. And here, just for simplicity, let's focus on the simplest topology, which is disk geometry. And for disk geometry case, area term can be explicitly evaluated, and which gives 2 pi times cos rho naught -1. And this area term can be re-expressed in terms of the corresponding gauge field, which denoted by this ball face number A, and whose value is given by cos rho -1 times d rho. And then this area contribution can be written in terms of boundary integral of this corresponding gauge field. And by Stokes' theorem, this boundary integral can be written in terms of volume integral of magnetic field B. So B is given by exterior derivative of gauge field A, and this expression gives us sinh rho times d rho times wedge d rho wedge d phi. And remember that for disk geometry, we had this background metric. So indeed, this sinh rho times d rho wedge d phi is indeed the volume element of this geometry. Therefore, this magnetic field B has a form of a constant times volume element. Therefore, this magnetic field is indeed interpreted as a constant magnetic field. So the area term basically gives us background magnetic field contribution. So in order to see next punctured disk case, it's also useful to express this area term in terms of this expression. So for disk geometry, on shell, this Rich scalar was just -2. So we can simply insert minus R over 2 inside of this definition of area term. And this expression can be written in terms of spin connection omega. However, this rewriting works only for disk geometry, and this rewriting does not work for the puncture disk geometry, because as we saw before, for puncture disk, this Rich scalar was not just -2, but it also had a delta function contribution. So this means that for puncture disk case, we should also expect some topological contribution for gauge field. So now let's look at this puncture disk geometry case. So first, to deal with original weird periodicity of angular coordinate, it's convenient to rescale the angular coordinate by this factor zeta, which brings the original periodicity 2 pi minus alpha to now the periodicity 2 pi. But this rescaling of the angular coordinate, of course, brings extra factor zeta square inside of this metric, new metric here. So we denote this new metric by tilde. And for this punctured disk geometry, we had on-shell action, which had area contribution and boundary circumference contribution. Here I excluded topological contribution, which is just constant and does not play any crucial role here. And this area contribution and boundary circumference contribution was written in terms of original coordinates before this rescaling. But we can also write down these contributions in terms of new rescaled coordinates. So that gives area contribution and boundary circumference contribution in terms of new rescaled coordinates. That's why we have a tilde here and here. But this rewriting also gives us additional contribution. And this additional contribution, when it's written in terms of boundary integral, this basically gives a pure gauge Aharonov-Bohm gauge field A of alpha, whose explicit expression is given by this equation. So we introduced, we rewrote the boundary action in terms of action for a quantum mechanical charged particle. So now we would like to solve such a quantum mechanical system. but we haven't yet carefully accounted the boundary condition yet. So here we need to take account of a boundary condition. So as before, we use the standard Dirichlet boundary condition, which is standard for ADS-CFT, which means that in this context, which means that we need to fix this boundary circumference Lm to a constant. So we insert a delta function which imposes this condition into the path integral. And then this constraint or this delta function basically reduces the previous square root type of relativistic line element to non-relativistic line elements, which are given by basically quadratic form of these coordinates. So, so basically, this rewriting is basically analogous to what we do for when we rewrite Nam-Goto string action to the Polytechnique string action. So for string theory case, we need to introduce world sheet metric to do such rewriting. But here we are talking about a point particle. So we need to introduce a world line metric. But such world line metric is basically fixed to constant by this condition. Therefore, we do not get any extra field after this rewriting, but we just simply re-express previous relativistic line element in terms of a non-relativistic one. So after this rewriting, we have this Lagrangian for disk geometry, and the corresponding Hamiltonian is given by this expression. So here we regard this bulk coordinates rho and phi as spatial direction, and these dots represents the derivative respect to the boundary time u. So in order to solve this system, we would like to solve Schrödinger equation, which satisfies this equation. And then the corresponding partition function is basically given by the vacuum diagram, which expressed in terms of this propagator. And this partition function can be also spectral decomposed. So here we parameterize energy by S²/2, and this rho of S is the spectral density. So in order to solve this system or this Schrödinger equation, it's first convenient to introduce a resolvent, which is given by this Legendre transform expression. And because of this e to the minus EU factor, this derivative respect to u just brings down this minus e. Excuse me. So therefore, this Schrödinger equation now becomes eigenvalue equation of this Hamiltonian H with eigenvalue given by this E. And such eigenvalue problem is actually solved explicitly. So the corresponding solution of this resolvent pi can be explicitly written in terms of this hypergeometric function. So here I introduced several notations. So B is related to Q by just factor I, and J is related to this energy E by this expression, and X is tangent square rho over 2. And here, the solution of resolvent pi, I set x prime equals 0, simply because this simplifies expression. However, we can also write down general expression for general x prime by using underlying global SL dual symmetry. So now we found this resolvent pi. We can obtain a propagator and also partition function and the spectral density. So the spectral density rho S is given by this change and cosine and cos expression. And this is exact expression for spectral density. We didn't made any approximation to solve this system. And the so-called Schwarzian limit is taking Q to infinite. This basically corresponds to the low temperature limit of the JT gravity. And in this limit, this spectral density is reduced to 2s times sinh 2 pi s. So we note that this expression in Schwarzian limit was previously obtained by various methods. For example, directly solving Schwarzian theory or dimensionally reducing from Levy theory or BTG black hole and so on. However, we note that this exact expression, which is valid for any temperature, is only obtainable in this charged particle picture. So this is one advantage of this picture. So next, let's we also look at puncture disk case. So for puncture disk geometry, we can also write down explicit Lagrangian and Hamiltonian. And for Hamiltonian, we have additional contribution, which is denoted by this GZ, which is related to this Aharonov-Bohm gauge field A of alpha by this boundary integral. So Hamiltonian is a little bit more complicated, but we can also use the previous technique to solve this system, and we can find exact spectral density given by this expression. We have a little bit complicated expression, but this is the exact expression for the spectral density. And in the Schwarzian limit, we have a simple cos form given by this expression. So again, we can obtain this Schwarzian limit expression by many other methods, as I said before. Same as disk geometry case, but this exact expression can be obtainable for only in this charged particle picture. So this is the advantage of this charged particle picture. So I had several pages for entanglement entropy, but I think I almost ran out of time. So maybe I can just go to conclusion.
Kenta, we have still time. If you would like, you can go ahead. You're
okay,
enjoying.
So yeah, sure. Okay, so I only have 3 pages, so it doesn't take much time. Okay, so let's talk about entanglement entropy for the for the Hartle-Hawking states defined on the previous geometries. So entanglement entropy can be computed by this Euclidean replica trick given by this expression, where this Zn is the nth replicated linear partition function. And for disk geometry, the linear partition function Zn is just shift inverse temperature by n times beta. So this means that if we use spectral decomposition expression, we just need to change this Boltzmann factor by e to the minus n times original factor beta times s squared over 2. So this means that spectral density does not change from the original partition function, which is denoted by Z1 here. Then we can simply use this replica trick expression for entanglement entropy. Then the entanglement entropy of Hartle-Hawking state of disk geometry can be expressed in terms of this expression. So this dimension of R is basically spectral density, and PS is given by this expression. Next, we would like to think about puncture disk geometry case. Puncture disk geometry case, so this replica number n appears for linear partition function, can be treated in the same way as we did for this conical defect angle alpha. Therefore, this puncture disk geometry case, actually spectral density also modified by this replica number n. But computation, excuse me, computation to get this replicated spectral density, basically we use the same technique as we did for conical defect angle alpha. So the resulting this spectral density is given by this little bit complicated integral expression, contains J, which is related to this parameter S by this expression. And Guzi we had previously, which is related to the Aharonov-Bohm gauge field. And these are just integration variable. So using this expression of spectral density, we can evaluate entanglement entropy. So here, just for simplicity, I already took Schwarzian limit corresponds to Q infinite. But we can also write down a general exact expression. But in this Schwarzian limit, we have entanglement entropy written in these simple expressions. So the first contribution is basically the same form as we had disk geometry case, but we also have extra topological contribution, which appears only for this conical, only for this puncture disk geometry case. So for first contribution, we call S1. For S1, we just need to replace the corresponding first order or non-replicated spectral density to the corresponding correct defect inserted spectral density, and then the rest of expression is basically the same as disk geometry case. So this S1 contribution in the semi-classical limit agrees with thermodynamical entropy, which is given by 2 pi minus alpha square times temperature. And this is basically a Bekenstein-Hawking entropy. However, for this puncture disk geometry, we had additional contribution, S2. And this S2 does not depend on temperature. Therefore, in the low temperature limit, because this S1 is proportional to temperature, low temperature limit, this topological contribution actually dominates over Bekenstein-Hawking entropy. So this is all for entanglement entropy. This is a final conclusion. So the first part of this talk, I will a little bit explain that if we define JT gravity by summing over all higher genus topologies, then the dual theory is actually a random ensemble defined by one Hermitian matrix integral rather than a specific quantum mechanical model defined on the boundary. So this is a first example of a new type of ADS-CFT correspondence, which involves some kind of averaging or ensemble or statistical ensemble for the boundary theory. And this type of duality might also hold for ADS3 pure gravity case, but I didn't mention a little bit anything. And then the second part, we discussed JT gravity on puncture disk, and I explained such a geometry naturally appears when we generalize the dilaton potential of JT gravity, and then we formulated such a deformed JT gravity in terms of standard quantum mechanical system with a constant background magnetic field plus pure gauge Aharonov-Bohm field. And then we solved such a quantum mechanical system exactly, namely not only Schwarzian limit corresponds to a low temperature limit, but also for generic temperature. And then we computed corresponding propagator, spectral density, and partition functions. And then finally, we discussed entanglement entropy of Hartree-Hawking states of this topology, and then we discovered some extra topological contribution that becomes dominant at the low temperature. Okay, so that's all for my talk, and thank you for your attention.
Thank you very much, Kenta, for the very nice and detailed talk. Thank you. And I think we have time for questions and comments. Please. Any question or comment? Can I ask a question myself?
Yes, sure.
Okay. I think according to what you said, if I have understood correctly, the dynamics of the boundary theory is still given by Schwarzian. Is it true so far?
Yes, yes, you can.
Okay, good. So we may expect to have a maximally chaotic quantum theory on the boundary. Is it still true?
Yes, that's true.
Okay, good. And okay, the next point is if the boundary theory is maximally chaotic, it means that even by changing the topology in the bulk, we have found some support for KSS bound. I mean, Mallasana, Schenker, Stanford. MSS bound. Then the question is this generalized JT gravity is some further example in support of that bound, or something that had been already predicted by those computations and theory?
That's a very good question, and thank you for bringing that point into this talk. So indeed, that's we also discussed in our paper, but unfortunately I didn't have time, so here I didn't mention anything about such chaotic behavior. So very interestingly, let's see. Sorry, I didn't write down explicitly. So this Schwarzian theory was actually only for disk geometry. So, and indeed for disk geometry, as you said, so if we, for example, include boundary operators, or for example, we couple this Schwarzian theory to some matter fields, and then if we study, for example, out of time of the correlator of such matter fields, then this Schwarzian theory actually gives a maximally chaotic behavior whose Lyapunov exponent is given by 2 pi times temperature. However, if we write down we can also write down Schwarzian theory for puncture disk geometry case. Such a Schwarzian theory actually reduce the Lyapunov exponent by this conical defect angle. So this means that if we couple to matter field, then if we couple matter field in this puncture disk geometry, actually they are not maximally chaotic, but Lyapunov exponent is actually reduced by this conical defect angle. And we can, in the paper, we also discussed dimensional reduction discussion. So probably you know that JT gravity, standard JT gravity can be obtained by a rotating BTZ black hole or near extremal BTZ black hole. Now, for this generalized JT gravity, we can actually obtain by dimensionally reducing the so-called SL2Z black hole, which is also a solution of pure Einstein gravity of ADS3, but boundary torus is actually twisted. Therefore, if you take near horizon geometry of such a black hole, actually reduces some conical defect angle when we consider two-dimensional theory. And then in the paper, we discussed again out of time order 4-point function of external matter field in this SL2Z black hole, and then we obtained the same result, namely the twist parameter in SL2Z black hole is related to the conical defect angle in two-dimensional theory or JT gravity, and under Lyapunov exponent in this SL2Z black hole background is actually reduced by this twist parameter of the SL2Z black hole.
And does it depend on the number of genus that we consider in the bulk or not?
So genus. So here I'm solely focusing on zero genus cases, and yeah. So this genus expansion we usually cut like this, and then just consider like this trumpet geometry, and this is okay for pure gravity case. But if we have a matter field, I guess we cannot do this kind of decomposition. And to be honest, I don't know what we need to do for matter couple case. So
I see. Thank you very much. Thank you. Okay. Any other question? Question or comment? Okay. Oh, Daniel, you have a question?
No, I was just sorry.
Okay, very good talk. Thank you again, Kenta. I think we can stop recording at this point. Then in the following, we can have some informal discussion if audience would like to do.